Hello everyone, I am Dr. Manju Gupta, Department of Chemistry, St. Aloysius College, Jabalpur. Today I am going to explain intensity and position of different functional groups in infrared spectroscopy. In the last lecture, we were discussing about a spring and ball model of a molecule. According to this model, the atoms are similar to the balls of different masses, and these atoms are connected by a covalent bond which is like an spring. And just like a spring, this covalent bond is always in a state of constant motion. The frequency associated with this vibration is known as vibrational frequency. If we apply radiation or energy in the form of light, the amplitude of a particular vibration may increase, and this leads to vibrational transition in the molecule. How much energy of the molecule absorbed by the radiation, it depends on the energy difference between the different vibrational energy levels. And for a particular bond, the frequency associated with the vibration is known as vibrational frequency, and it is denoted by or explained by Hooke's law. The value of vibrational frequency depends on bond strength, that is K, force constant, and reduced mass, that is mu. Mu is equal to m1 m2 upon m1 plus m2, masses of two atoms, m1 and m2. So vibrational frequency mu bar can be calculated by Hooke's law by this equation. In this slides, there are several functional groups and what will be the value of vibrational frequency on the basis of their reduced mass and force constant. The value of force constant for single bond and for double bond and triple bond just increases. For OH group, the value of vibrational frequency is 3600 centimeter inverse. For NH, it is 3300 centimeter inverse. For carbon-hydrogen stretching, it is 3000 centimeter inverse. For carbon-carbon stretching, it is 1100 centimeter inverse. For carbon double bond carbon stretching, the value of vibrational frequency is 1650 centimeter inverse. For carbonyl group C double bond O, the value of vibrational frequency is 1725. For carbon triple bond carbon, the value is 2100 centimeter inverse. And for cyanide or nitrile or C triple bond N group, the vibrational frequency is equal to 2350 centimeter inverse. These values are known as basic values because these values are calculated on the basis of reduced mass and force constant values. But practically, when in the IR spectrum, the value of vibrational frequency may differ from the base value. This slide shows typical infrared absorption region for different functional groups. In between 4000 centimeter inverse to 2500 centimeter inverse, OH stretching, CH stretching, and NH stretching. These three functional groups with stretching vibration shows absorption in this region. Within 2500 to 2000 centimeter inverse, C triple bond N, nitrile, C triple bond C, or any other unsaturated molecule with heteroatom may show band. In between 2000 to 1800 centimeter inverse, very few bands are observed, which is not characteristic of a particular group. 1800 to 1650 centimeter inverse, this region is most important region of IR in which carbonyl C double bond O stretching is observed. In 1650 to 1550 centimeter inverse, C double bond N, C double bond C, and N double bond O, these functional groups show absorption. Below 1550, the region is known as fingerprint region. from 4000 to near about 400 centimeter inverse, the region is known as group frequency region, since most of the functional group shows absorption in this region. And 1400 to 900 or 650 centimeter inverse, the region is known as fingerprinter region. Why it is known as fingerprint? Because it is the characteristic of the compound. Position of the band in between 4000 to 400 centimeter, where the compound show the absorption. It depends on the reduced mass and the value of force constant, which can be calculated by Hooke's law. But the intensity of the band will be sharp, medium, or weak. The intensity of the band depends on the fluctuating dipole moment of a particular functional group. As the value of fluctuating dipole increases, the intensity of the band increases. Here you can see 3 IR spectra: ethanol, 1 propanol, and 2 propanol. Since IR spectroscopy is used for the detection of functional group, in all the 3 compounds, there is the same functional group, alcohol. And in all 3, this broad band represents the OH stretching in the molecule. If it is the same in all the 3 compounds, then how we can differ which is ethanol, which is 1 propanol, and which is 2 propanol? For this is the same functional group region. Here you can see after 1500 centimeter up to 1500, that means in the group frequency region, the shape of the spectrum and the position of the band is similar. But below 1500 centimeter inverse, there is the changes in the spectrum. That's why the region from 400 to 1500 is used for the diagnostic of the compound or functional group, and below 1500, this region is known as fingerprint region, which is the characteristic of a compound. Now we discuss the position of different functional group bands in IR spectrum. First, we are taking position of CH band. Since we are discussing organic compounds, and in organic compounds, the backbone or the main unit is the carbon, and carbon is always associated with hydrogen. So position of CH band in IR spectrum. When we calculate the position of CH band or the value of vibrational frequency for CH band by Hooke's equation or Hooke's law, the value of CH stretching vibration is 3000 centimeter inverse, which is known as the base value. But this carbon-hydrogen stretching may observe in different type of organic compounds. First, we are taking alkynes. In alkynes, triple bonded carbon is attached with single bonded hydrogen. The state of hybridization of the carbon is sp hybridized. Base value is 3000 centimeter inverse, and alkyne show absorption at 3300 centimeter inverse when the carbon is sp hybridized. Sp hybridized carbon hydrogen stretching show absorption at 3300 centimeter inverse. Next, alkene or aromatic carbons. In alkene or in aromatic carbon, both are sp2 hybridized. sp2 hybridized carbon, when attached with the hydrogen, then it absorbs light of frequency of 3100 centimeter inverse. Saturated compounds, alkane. In alkane, single bonded carbon and hydrogen, CH stretching, sp3 hybridized carbon. This shows absorption at 2900 centimeter inverse. Here we can give a thumb rule. As we going from sp3 to sp hybridized carbon state, the percentage of S character in the molecule increases, and as the percentage of S character increases, the value of vibrational frequency increases. From alkane to alkyne, the percentage of S character increases. That's why the value of vibrational frequency increases from 2900 to 3300 centimeter inverse. So in case of alkane, alkyne and alkene, base value is 3000 centimeter inverse. Alkane shows absorption below 3000. Alkene and alkyne shows absorption above 3000. Aldehyde. Aldehyde functional group is CHO, carbonyl attached with single hydrogen and one alkyl group. This CH band, which is also sp2 hybridized carbon, it shows two bands at 2870 centimeter inverse and 2720 centimeter inverse. All these four vibrations are stretching vibrations. Other than this, CH2 bending vibrations are observed near 1465 centimeter inverse. This is the spectrum of alkane, octane, in which CH stretching, which is sp3 hybridized. It is below 3000 because of carbon hydrogen stretching at 2940. And second is at about 1470 centimeter inverse. This is because of the CH bending. So in case of alkene, only we have to see where is the carbon hydrogen stretching and where is the carbon hydrogen bending. This is the spectrum of alkene. CH. Carbon is sp2 hybridized. The molecule is octene that has sp2 and sp3, both type of carbon hydrogen bonds. Below 3000, we observed sp3CH stretching. Above 3000, sp2CH stretching. At 1400, CH bending, and this is near about 1550. This is C double bond C stretching. So in comparison of alkane and alkene, sp3 hybridized carbon shows absorption below 3000, sp2 shows above 3000. This is the spectrum of alkyne 1-octane, in which carbon is sp hybridized. Here you can see at 3300 centimeter inverse, approximately, there is triple bonded carbon hydrogen stretching. The molecule has sp3 hybridized carbon. So below 3000, this is single bonded CH stretching. Carbon triple bond carbon stretching observed nearby 2100 centimeter inverse. And at 1400, these are the CH2 bendings. Now, there are two main things. Since the intensity or the selection rule of the IR depends on the fluctuating dipole moment. In case of symmetrical alkynes are always IR inactive. The C triple bond C stretching only observed in unsymmetrical alkynes. In case of symmetrical alkynes, the dipole moment, the value of fluctuating dipole moment will be 0 and the particular band will be IR inactive. Similarly, in case of triple bond CH hydrogen, only the terminal alkynes where the last carbon has triple bond, that has hydrogen. So only in case of terminal alkynes, CH stretching band can be observed. In case of internal alkynes, both the triple bonded carbon atom will be attached with the alkyl groups. So carbon hydrogen, triple bonded carbon hydrogen stretching will not possible. These are the two main things in case of alkynes. About the carbon triple bond carbon, this will be observed only in case of unsymmetrical alkyne and triple bonded carbon hydrogen. Sp hybridized carbon hydrogen stretching which observe nearby 3300 centimeter inverse only in case of terminal alkynes. This is the spectrum of aromatic compound toluene. In case of aromatic compound, one group is aromatic, that is C6H5, and one aliphatic chain CH3 is attached. All the 6 carbon of benzene are sp2 hybridized, so they show absorption above 3000, while CH3 of toluene is sp3 hybridized and it shows absorption below 3000. You can see here at 2925, this is CH stretching because of this methyl group, and these are the two vibrations above 3000 at 3099 and 3068 centimeter inverse. This is because of CH stretching of aromatic ring. Other than this, 1614 centimeter inverse. 1614 centimeter inverse, this band shows the presence of carbon double bond carbon stretching. At 1506 centimeter inverse, carbon stretching, carbon single bond carbon. And in the fingerprint region, of aromatic compounds, there are several peaks are present. 2, 3, 4, 5, some particular peaks and very sharp peaks will be present in the fingerprint region. As at 738 centimeter inverse, CH banding, this is known as OP vibration, out of plane vibrations of CH bond. Now we come to the second functional group, position of OH band in IR spectrum. OH is also an important functional group which can be detected by IR spectrum. Oxygen-hydrogen bond or oxygen-hydrogen stretching band observed in alcohols, phenols, and carboxylic acid. Alcohols ROH, phenols C6H5OH, and carboxylic acid RC double bond OOH. In all 3 class of compounds, OH bond is present, so OH stretching vibrations may be possible. The position and shape of OH band depends on the strength and the actual nature of the hydrogen bond or OH bond. The free OH group shows absorption at 3600 centimeter inverse and produce a sharp band. This is the free band of free OH band. Whereas bonded OH band shows a broad band from 3300 to 3600 centimeter inverse. What do you mean by free OH and bonded OH? Both are oxygen-hydrogen bonds, but what do you mean by free OH and what do you mean by bonded OH? The meaning of bonded OH, as we know in alcohols, hydrogen bonding may be possible. Because of these hydrogen bonding, the molecules are associated with each other. So these are known as bonded OH. Bonded OH groups shows absorption at 3300 to 3600 centimeter inverse and produce a broad band. And free OH means when alcohols are in vapor state or the solution of alcohol is very dilute. That means the molecules of the alcohols are far apart from each other. There is no intermolecular interaction. On going from free OH to bonded OH, 2 changes may observe. 2 changes are taking place. First is frequency shift. OH absorption shifted from 3600 to 3300 centimeter inverse. And second thing is the sharp band converted into broad band. What is the reason of frequency shift? why the value of OH stretching vibration in free OH compound is 3600 and why in hydrogen bonded compound it is 3300 centimeter inverse. In case of intermolecularly hydrogen bonded compound, the same OH bond is involved in the hydrogen bonding. So the bond strength between the oxygen and hydrogen bond will be decreases. As the bond strength decreases, the value of force constant decreases and it will result in the decrease in value of vibrational frequency. That's why the value of vibrational frequency from free OH to bonded OH shifts from 3600 to 3300 centimeter inverse. What is the reason of the change of shape of the curve? Why it is broadened? When the molecule is hydrogen bonded, in case of hydrogen bonded and these are connected to each other, oxygen and hydrogen, several molecules are connected by oxygen and hydrogen and they may have different force of attraction, that means different value of force constant, so they may absorb different amount of energy. Because of several molecules present in the intermolecular hydrogen molecule and they absorb different radiations because of the strengthening of the bond. So it will result in the broadening of the band. These are the two important parameters of free OH and bonded OH. Now we come to the example. This is the simple spectra, a simple IR spectra of 2-butanol in which you can see below 3000 there are CH stretching and above 3000. Above 3000 it is bonded OH. When it is broad, the OH group will be bonded. That's why that shows 2-butanol molecules are intermolecularly hydrogen bonded. 2-butanol, this spectrum is scanned in the solution state or the concentrated solution of the 2-butanol. If we take any alcohol in two different states, here you can see the two spectrums of ethanol. Spectrum in blue, it is the spectrum of ethanol in solvent, in suitable solvent, and second, when the spectrum of ethanol was scanned in vapor state. In vapor state, there is no intermolecular attraction between the ethanol molecule. That means there is no intermolecularly hydrogen bonding. Whereas when the ethanol is in any solvent or its concentrated solvent solution, there is intermolecular hydrogen bonding between the ethanol molecules. So it will result in the broad band near about 3300 centimeter inverse. And when the ethanol spectrum is taken in a vapor state or with very dilute solution, the free OH shows absorption at 3600 centimeter inverse. So this is the difference between the concentrated solution of alcohol and the dilute solution or vapor states spectrum. Here you can see the effect of dilution on OH band. When we take concentrated solution or the pure liquid, in case of pure liquid, pure ethanol suppose, all the alcohol molecules are strongly intermolecular hydrogen bonded. When they are strongly bonded, hydrogen bonded, then only a broad band will observed at 3300 centimeter inverse. When we start to dilute the solution, some molecules are still intermolecularly hydrogen bonded, some becomes free. That's why we observe both the peaks. This sharp peak because of free OH, this broad band because of bonded OH, intermolecular bonded OH. And this is CH stretching. And in case of very dilute solution or when the solution is scanned in the vapor phase, all the molecules becomes free. There are no intermolecular attractions between the molecule. So in this case, only OH stretching observed because of free OH bond. So here you can see the effect of dilution or effect of concentration. Here we can conclude intermolecular hydrogen bonding is depend on the concentration, its shape and its absorbing value, both depending on the concentration of the alcohol solution. Second example is example of molecules in which intramolecular hydrogen bonding is present. Intramolecular, that means two groups in the same molecule are connected to each other by intramolecular hydrogen bonding. This is the example of orthonitrophenol, in which OH, hydrogen of OH group, hydrogen bonded with the oxygen of nitro group. So this bond is intramolecular hydrogen bonding. In the same molecule, two groups are connected to each other. In case of intramolecular hydrogen bonding, again there is no association, no intermolecular attraction, only the bonding is present in the single molecule. So intramolecular hydrogen bonded compound shows absorption similar to the spectrum which is scanned in the vapor phase. This is the sharp peak which is observed by intramolecular OH bond. So here you can see, since the bonding is involved in the same molecule, within the molecule between the two groups, so if we dilute the solution or if we increase the concentration, the bonding between the group will not affect. So we can say intramolecular hydrogen bonding is not concentration or dilution dependent. Next functional group is position of NH band in IR spectrum. Nitrogen and hydrogen. Again, the electronegativity difference between nitrogen and hydrogen is very large. So the band produced by the NH stretching mode will be sharp. NH stretching of band shows absorption in between 3300 to 3400 centimeter inverse. NH band can be present in primary amines or secondary amines. In case of primary amines, this single nitrogen is attached with two hydrogens. There are two NH bonds and two types of stretching of vibrations are possible: symmetric stretching and asymmetric stretching. So primary amines gives two peaks, symmetric and asymmetric. Secondary amines only have one NH bond, so it produces one peak, and tertiary amines gives no peak. If we take the example of primary amine, this is 2-amino butane, in which second position NH2 is present as the primary amino group and remaining hydrocarbon chain is present. Remaining hydrocarbon part shows absorption below 3000 centimeter inverse. This is CH stretching, banding at 1400 centimeter inverse, and NH2 NH2 primary amine group shows two peaks near about 3300 centimeter inverse. These are the two peaks, two NH bands, one at 3369 centimeter inverse and another at 3299 centimeter inverse. This is because of the NH banding vibration, and this is this is because of NH stretching vibration, and at 1600 this peak is because of NH bending vibration. In case of secondary amine, the example of secondary amine is N-ethyl benzene. Out of one of the hydrogen of NH2 is replaced by any alkyl group, so it is converted into secondary amine. Nitrogen is connected with the only one hydrogen, so it will produce only one NH band. This is one NH band at the same value, near about 3300. One NH band observed at 3403 centimeter inverse. In case of NH2, two peaks or doublet will be observed near about 300. In case of secondary amine, only one peak will be observed. In case of tertiary amine, since there is no NH bond, so there is no absorption in the range of 3300. NH stretching band in tertiary amine, it is totally absent. This is the example of N-dimethyl aniline. N-dimethyl aniline, in which nitrogen is attached with two alkyl groups, and both the alkyl groups shows absorption below 3000 centimeter inverse. These are the peaks produced by CH3 groups, and above 3000 these peaks are produced by benzene ring. Thank you.